Alright, so it is time to do part B for homework 3, process dynamics and controls. And what we're going to do this time is derive a closed loop transfer function for 3 identical gravity drained tanks in series, using a proportional only controller to start off a little bit more simple. That will manipulate the flow into the first tank in order to control the liquid level of the last third tank. And I'm going to get into that now. To make sure that I wouldn't forget the diagram this time, beforehand I just went ahead and kind of made this blank slate diagram. But as you can see, we have our 3 tanks, 1, 2, 3. We have our flow rate going in and our height coming out, which we talked about in part A, but for 1 tank. Coming out of tank 1, we will have an H1, that's the height of the liquid water in tank 1, coming and flowing into the next tank. After it goes through this right here, which we'll talk about later, it's our Q in to tank 2, so that's Q1. Similarly, coming out of tank 2, H2, same thing there. Eventually it is the Q into tank 3, which is Q2. And we don't have another tank after that, so what we have is our measured variable H3. And we want to look at H3 and alter the flow in eventually so that we can hit our goal, essentially. We're going to say that the transfer function for each of the tanks is going to behave like K over tau s plus 1, K being the gain and T being the time constant. So that's the same for all of them because they are identical. If they were not identical, that would be a different story. And then getting from the height to the flow rate, we have a 1 over K, or the inverse gain right there. And again, that's the same for both of those. So we've filled in our diagram that I wrote out, and now what we want to do is basically derive the transfer function that covers the entire thing, taking from these pieces that I wrote in. And luckily it's pretty simple. We actually say that this H3 is equal to each of these boxes that I have, each of the transfer functions multiplied together. So we know we have 3 of the K over tau s plus 1, and we have 2 of the 1 over K. So I'm just going to cube and square those. And then we actually also have the flow rate in the Laplace domain. And then if we were to multiply that out, we would have 1K left in the numerator, the Q in, and then this would all be over tau s plus 1 cubed. And we're going to call the process, this is the process transfer function. Except we have that Q in on the side. Kind of like in part A, we had this equation just be the 1 over a s plus all of that multiplied by the q in. but we are on part B, so write that out here. And that's because this QN is entering initially. It is not a part of this network right here. And we have to keep in mind that we are doing a closed loop transfer function here. Basically what that means is we have continuous feedback going in a loop in order to reach our set point. So we would have our H3 set point going into the process. We would have a comparator here that will increase or decrease based on the difference between H3 and H3 set point. So how far you are from where you want to be. This right here is the error. This GP is actually represented by this whole thing right here that I just boxed in. And coming out of here would be H3. We want to keep in mind we are doing closed loop control, so we have a feedback back to the start. We could also, technically we should put in a GM, and basically this represents the lag of the sensor. So for a simple case, we're going to say that there's no lag at all and that this is equal to 1. So we don't really need to take that into account. But in the real world, your sensor is going to have some lag to it. That's going to influence that loop. And so basically what this means is we're saying that it's an instantaneous sensor. So as soon as the sensor senses what the height is, it'll immediately go through that loop. And so to define the error, that error is simply the difference between the set point of the height and the actual height that we're reading. And so according to this, we know that our H3 should be equal to our process transfer function that we derived here times Kc. This is the proportional controller gain. And this is a proportional only controller, so we're just going to include that. And then we also want to multiply by this error that we have. And taking what we wrote from above, we have the process transfer function multiplied by the proportional controller gain times the error, which, as I said above, is the difference between the set point and the actual reading. Now to isolate this H3, we want to isolate that H3 so that we can have it on one side of the equation. And then we get this on the left-hand side. On the right-hand side, we have the Kc GP times the height set point, which gives us H3 equal to Kc GP divided by the 1 plus Kc GP, all multiplied by the set point. And then we can substitute in what we calculated for the transfer function, the process transfer function. And I accidentally erased this, but up here we had our process transfer function It's actually tau s, so k, the gain, over tau s plus 1 cubed. That right there is what we want, and the q in is not included in that. I think I said that earlier, but I also think I wrote it down there, which would not be correct. But as I was saying, we can rewrite this and substitute in that GP that I calculated. And we then get that the liquid level height of tank 3 is equal to KCK over our tau s plus 1 cubed. And then we are adding the KCK. So that is from that step to this step. And we still need to multiply by our set point for the height. And this right here is the equation that we want to use for the transfer function. And I do want to note that if that sensor feedback was not instantaneous, then we would have our height, our H3 would be equal to KC GP over 1 plus KC GP GM. So that is this same thing, except we literally just multiplied the denominator by, well, a piece of the denominator by the GM transfer function. But we are assuming that our sensor is instantaneous, so we don't need to take that into account right now, but it is something I wanted to cover. Now for part 2, we are going to use the final value theorem to show that with a proportional only controller, the height of the third tank will always exhibit an offset relative to the set point that reduces with an increase in gain, which was our KC. That's our gain for the proportional controller. And we covered this in, I think, homework 1, but that offset is just inherently what happens when you have a proportional only controller. And so down here I wrote the final value theorem out, but this y is our Laplace domain, and then this is it prior. Basically, we're switching it from being in terms of t to being in terms of s. So this holds true. We want to take our transfer function so that we can take our overall transfer function so that we can, and everything here is actually in the Laplace domain except for our H3 set point, which in the Laplace domain is equal to a over s. So then we can rewrite that as a over s. And I'm just going to put it in the numerator. Same denominator, no change there. And now what we want to do is take the limit of that as s approaches 0. The limit as s approaches 0 for this right here We knew that this is going to be the steady state height. We get our kck over our 1 plus kck that we have here times a. And that is basically getting rid of the s's right there. We know that the offset is going to be a minus the steady state. So kind of like what we did in part A, if I can find it, kind of with our deviation variables. This is our steady state. And that's equal to a minus this kck times a over 1 plus kck. And then to get a common denominator, we're just going to multiply by the 1 plus kck in the denominator. And from this a right here, we have a 1 plus kck over 1 plus kck. And we need to subtract right there. So our offset for this proportional controller is equal to this right here. To simplify this, we have a 1 plus kck, we're subtracting a kck, so we would have a times 1 over 1 plus kck. And as you can see, as we increase kc, that would result in the offset decreasing. But sometimes, depending on your simulation, that can make things unstable, so that's why we introduced in previous homeworks some other controllers, particularly the integral controller. But for now, this is okay. This represents our offset in the Laplace domain. And this right here was our transfer function. And yeah, so we derived our closed loop transfer function for those 3 identical gravity drain tanks in the form of manipulating the flow into the first tank right here to get some liquid level in the third tank. We had our process transfer function that we labeled GP right here in our diagram. And then after we looked at the full diagram for our closed loop transfer function, we were left with this transfer function equation. And this describes how the height in the third tank changes with these variables. So remember, our Kc is the proportional controller gain. K is the general process control gain, or I guess the general process gain that was inherent to the processes. Remember how each tank was K over tau s plus 1. Tau is our time constant. And H3SP was our height 3 set point. And finally, we went over Final Value Theorem and showed that offset again that we see with a proportional only controller. There would still be some small offset if we had an integral controller as well, but it would be much less than the proportional only just by itself. Very abrupt transition to the outro, but thank you for watching. The next video is going to be part C, where we're going to use the Routh-Hurwitz criteria in order to find the maximum proportional controller gain in relation to the process gain for these same 3 identical tanks. And so we're finally getting into how to actually calculate the maximum proportional controller gain rather than just trying and testing like we did in previous homeworks. And look forward to that. Thanks again.